Welcome back to the Deep Dive. Today, our mission is, well, pretty straightforward. Cut through the noise on sustainable materials and give you the need to know. We're zooming in on composites, specifically looking at a huge problem with one of the world's most promising green materials. I'm talking about bamboo.
Yes, bamboo. It really is quite something. It's, everywhere, grows incredibly fast.
Like ridiculously fast.
Exactly. And its strength-to-weight ratio, fantastic. Makes it theoretically perfect for lightweight structures, replacing petrochemical-based stuff.
But here's the twist, what we're calling the bamboo paradox. It seems perfect, but it has this one, killer flaw. It really doesn't like water.
That's the core issue. It's inherent hydrophilicity. It just wants to soak up moisture.
Why is that?
It's down to the cellulose structure. All those hydroxyl groups, they're like little magnets for water molecules. The fibers essentially act like sponges.
Which is obviously bad if you're expecting it to hold something up.
Definitely. Water absorption leads straight to degradation. The fibers swell, they lose their bond with the matrix, which is usually hydrophobic, like epoxy.
So they just don't stick together anymore.
Pretty much. And you see this massive drop in mechanical strength. Tensile, flexural, it all just plummets. The structural integrity basically vanishes when it gets wet.
Okay, so the problem is moisture. The solution needs to be some kind of water barrier. But crucially, we want that solution to be as sustainable as the bamboo itself, right?
That's the goal.
So this brings us to a really interesting 2026 study by Madhusudhana and colleagues. They explored using, get this, waste from the seafood industry, specifically particulate filler made from ground-up clamshells.
Right, using that waste to build the water barrier within the composite.
Exactly. The study aims to see if this specific bio-waste can seriously boost the durability, the strength retention of these bamboo-epoxy composites after they've been soaked in water.
It's a fantastic example of, the circular economy meeting material science. And it's tackling a well-known problem.
People have tried other things before, haven't they?
Oh, absolutely. Researchers have been working on this for a while. Common strategies include chemically treating the bamboo fiber surface, maybe with something like NaOH, sodium hydroxide.
To make it less water-loving?
Sort of, yeah.
Yeah.
To reduce those active hydroxyl groups. Or another approach is hybridization, mixing the bamboo with synthetic fibers. Think glass or carbon fibers.
Which works, I guess, but then you lose the whole green and low-cost angle pretty fast.
Completely. That's the trade-off. So the third route, which often shows a lot of promise, is adding fillers directly into the polymer matrix, the epoxy in this case.
How do fillers help?
Well, they work in a few ways. They physically occupy tiny gaps, these microvoids, inside the composite. They also act as barriers, blocking the paths water would normally take to seep in.
Okay.
And importantly, they can actually improve the interfacial adhesion, that bond between the fiber and the resin we were talking about.
Right, the bond that water usually destroys.
Exactly.
Now, the literature often mentions synthetic fillers for this, doesn't it? Like high-tech ceramics.
That's true. Things like silicon carbide, CRD or aluminum oxide, alloduroo, they definitely reduce water absorption. We've seen studies showing that.
But again, not very sustainable or cheap.
Not at all. And that's why there's this big push now towards, waste valorization, using stuff that's already out there.
Right.
Agro waste, industrial byproducts.
Like what? Eggshells?
Eggshell powder, yeah. Fly ash from power plants,
yeah.
xenospheres. People are trying all sorts of things.
Which leads us neatly back to clamshells. Why these specifically? What makes them stand out from, say, eggshells?
Well, firstly, clamshells are a massive global waste stream from the seafood industry, just tons of stuff. But the key is their chemistry.
Okay.
They're mostly calcium carbonate,
Yeah.
CoO. And that specific compound has some really useful properties. It's naturally hard, has extremely low solubility in water.
So it doesn't dissolve or absorb water itself?
Right. And it turns out it has really good compatibility with polymer matrices like epoxy. It mixes in well. So you're essentially adding this fine, non-absorbent mineral powder that acts as both a physical block and chemically, it just doesn't interact negatively with water.
A perfect barrier, basically, made from garbage.
Pretty much. High-quality garbage, as you say.
Okay, let's get into the practical side. How did the researchers actually turn seaside waste into a usable engineering material?
The process itself is fairly straightforward, which is important for keeping costs down. They collected discarding clamshells, in this case, from coastal Karnataka in India.
Had to clean them thoroughly, I imagine.
Oh, yeah. Washing, drying, sometimes soaking in hot water to get rid of any residual organic bits. You need a clean starting material.
And then the grinding.
Then the grinding,
Sure.
brushing, followed by milling in a ball mill. That's pretty standard industrial tech. The crucial part here is getting the particle size right,
Why is size so important?
because it affects how well the filler disperses in the epoxy and how much surface area is available to, interact and form that barrier. Too big and it's not effective. Too small and it can clump up.
So they targeted a specific size.
They did. They sieved the powder to get particles mostly in the 50 to 75 micrometer range.
Yeah.
50 to 75 manner.
Okay.
And to double check, they weren't just grinding up random beach stuff. They did an elemental analysis, EVX.
Ah.
I confirmed calcium was the main element, about 50% that weight, which lines up perfectly with a high purity calcium carbonate composition. So they verified their waste stream was actually consistent and suitable.
Good stuff. So consistent bamboo, consistent filler. How did they put it all together in the composites and test them?
Right, so the bamboo fiber content was fixed 35 weight percent for all samples. They then made 4 different batches. One was the control, just bamboo and epoxy, 0 filler.
The baseline.
The baseline. Then they made 3 hybrid composites, adding the clamshell powder into the epoxy at different levels, 3%, 6%, and 9% by weight.
And the big test was chucking them in water.
Essentially, yes. They followed the ASTM D570 standard procedure, immersed the samples in fresh water, room temperature, and just left them there.
Until they couldn't soak up any more water.
Exactly. Until they reached saturation, they monitored the weight, and when the weight change was less than 0.1% for 3 days straight, they called it saturated.
Then pull them out and immediately test the strength.
Pull them out and straight onto the testing machines. Tensile tests pulling them apart and flexural tests bending them. ASTM standards again, D3039 and D790. This really simulates how they'd perform under load when wet or damp.
Okay, moment of truth. Did the clamshells actually work as a barrier? What did the water uptake results show?
They absolutely did. It was quite clear. The unfilled composite, the control, soaked up the most water, as expected 5.85% of its weight. That's our benchmark failure point.
And the ones with the filler.
As soon as they added the clamshell powder, water uptake dropped. But here's the interesting part. There was a definite sweet spot.
Oh. More wasn't just better.
No. The sample with 6 weight percent clamshell filler showed the lowest water uptake, only 4.07%.
Wow, okay. How much better is that compared to the control?
That's a 30.4% reduction in water uptake, just by adding 6% of this waste powder.
30%. That's a huge improvement. But hang on, you said it wasn't just more is better. What happened at 9% filler?
Right. This is really important. At 9% loading, the water absorption actually went up slightly to 4.95%. Still better than the control, but worse than 6%.
Why would that happen?
It suggests that at that higher concentration, the filler particles start to clump together. We call it agglomeration. The epoxy just can't wet out and disperse that much powder evenly.
And the clumps, they cause problems.
Yeah, these clumps can actually create tiny new voids or weak points at their interfaces, paradoxically giving water new little pathways to sneak in. So 6% was the optimal loading here.
Okay, 6% is the magic number. How does that 30.4% reduction stack up against those fancier synthetic fillers you mentioned earlier?
Very favorably, actually. That 30.4% reduction with 6% clamshells was reported as being better than what similar studies found for ceramic fillers, like aluminum oxide, which gave around 25.6% reduction, and silicon carbide, which is about 22%.
So literally getting better performance from waste than from expensive, energy-intensive ceramics.
In this specific context for water blocking, yes. It's quite remarkable.
Okay, that's the water uptake. But the real question is, does less water mean more strength when wet? Connect the dots for us.
That's the crucial link. Let's look at the control sample again, the one that soaked up 5.85% water. When tested wet, its strength just collapsed.
How bad was it?
Compared to its dry strength, it saw a 52% reduction in tensile strength and a 43% reduction in flexural strength.
Yeah.
Basically cut in half or worse.
Ouch. That really highlights why untreated bamboo composites aren't used outdoors.
Exactly. The water softens or plasticizes the epoxy matrix, and it swells the fibers, wrecking that crucial fiber matrix bond. But the 6% filler composite, a completely different story.
The champion. How did it hold up when wet?
It showed by far the best strength retention. Its maximum wet tensile strength was 31.5 megapascals, and its wet flexural strength hit 61 megapascals.
Okay, those are the numbers, but how much better is that compared to the wet control sample, the one that fell apart?
That's where it gets really impressive. Compared to the wet unfilled composite, the 6% clamshell formulation boosted the wet tensile strength by 68.4%.
68%.
And the wet flexural strength by 52.5%.
Wow. So the mechanism is?
The clamshell particles act as that barrier, reducing the water getting in. Less water means less fiber swelling, less plasticization of the epoxy, and critically, it maintains the integrity of that interface, allowing the composite to actually transfer load effectively even when wet.
Okay, a 68% improvement in wet strength retention is, well, that's game-changing, isn't it? What does that actually mean for someone listening? What could you do with this material now?
It fundamentally expands the possibilities. Before, you were pretty much limited to dry, indoor uses, maybe some decorative panels. Now, with this demonstrated durability against moisture, bamboo composites using this approach could realistically be considered for semi-structural outdoor applications. Think about things like architectural panels, maybe some types of decking or durable outdoor furniture, even potentially certain components in transportation cars, buses, where things inevitably get wet sometimes.
So it moves from a niche eco-material to something potentially much more mainstream and industrial.
That's the potential, yes. Solving that key durability flaw opens up a much wider range of applications.
The numbers are definitely convincing, but, sometimes seeing is believing. Did they look at how the materials actually broke? The visual evidence?
They did, yeah. Using scanning electron microscopy, SEM, to look at the fracture surfaces after the tests. Fractography.
And what did the failed control sample look like under the microscope?
It was exactly what you'd expect given the poor performance. The micrographs showed clear signs of moisture damage. The matrix looked degraded. You could see where the fibers had obviously swollen up. And there were large gaps around the fibers, indicating debonding. Lots of evidence of fibers just being pulled right out of the matrix rather than breaking with it.
So total failure of adhesion. Looks rough and messy, I bet.
Very much so. A clear picture of poor load transfer because the water just destroyed that interface. Now, compare that to the optimal 6% filler composite.
What did that look like?
Much, much cleaner fracture surface. Far fewer signs of fiber pullout, less obvious matrix degradation. Crucially, you could actually see the little clamshell particles embedded uniformly within the epoxy.
So they weren't just floating around, they were properly integrated.
Exactly. They seemed well dispersed and bonded within the matrix. This suggests much better wetting of the fibers by the resin initially, and a stronger interfacial bond overall, thanks in part to the filler.
So the filler is not just blocking water, it's also kind of physically reinforcing that connection.
That seems to be the case. It contributes to a stronger, smoother interface that can handle higher loads and, critically, maintain that ability even after being soaked. The visuals really back up that 68% jump in wet strength.
Okay, let's wrap this up. The main takeaway for you listening seems crystal clear. This study strongly suggests that waste clamshells are not just viable, but actually a highly effective, sustainable, and potentially very cost-effective filler for bamboo-epoxy composites. Specifically, that 6-weight% loading hit the sweet spot, dramatically improving durability and structural stability in wet conditions.
And looking at the bigger picture, this kind of research really validates using high-quality waste streams like these shells as a serious alternative to traditional, often expensive and non-renewable reinforcements. It's a solid step towards, genuine waste valorization and building a more circular economy in manufacturing materials.
Definitely feels like a win-win. Good performance, low cost, and better for the planet. But the researchers themselves pointed out a couple of limitations. They only used one particle size range, that 50-75 micron window, right? And they only tested it in fresh water.
Yes, standard lab conditions.
So that leaves us with a final thought, something for you to ponder. If these waste clamshells work this well against plain old fresh water, what might happen if we push them harder? What if these composites were exposed to more aggressive real-world conditions, like prolonged immersion in salt water, which is highly corrosive, or maybe exposure to alkaline solutions found in some industrial settings, or even concrete contact?
And what about the filler itself? Could we fine-tune it? Maybe combine these micro-sized particles with even smaller, nano-sized waste fillers? Could that unlock even greater levels of durability?
Lots to think about there. Definitely fertile ground for future work. Thanks for taking this deep dive with us today.
My pleasure.
We'll see you next time.